work was performed at Case Western Reserve University and was funded by NASA. It was done like 8 years ago. I designed a high temperature wide bandwidth SOI-CMOS transimpedance amplifier, and then this amplifier was used for application to capacitive temperature sensing. And the high temperature electronics have various applications such as aerospace, automotive, and geothermal. For high temperature design, the challenges for MOSFET starts around 200 degrees C. The most important effect is the reverse bias junction leakage, which from room temperature to 300 C increases by a couple of orders of magnitudes, which might cause latch up or some leakage in the dynamic nodes of the circuit, and also it reduces your bias current. The second effect is the decreased mobility. Your mobility decreases, your GM goes down, so from room temperature to 250, your mobility goes less than half. And then your threshold voltage varies. For NMOS, it goes down by 2 millivolts per degree, and for PMOS, it goes up by 2 millivolts. Now I'm going to talk about the transimpedance amplifier that we used that works up to 300 degrees C. Now, originally this amplifier, I designed it to be able to make an oscillator using a MEMS resonator, which has a series resistance of a couple of mega ohm. And so, when you design an oscillator, you don't care about first the loop gain, and you just make sure that it's greater than 1. And so this amplifier actually, its gain varies with temperature and process. So for capacitive sensing, so the resistance needs to be calibrated. So this is the first stage of this amplifier. So this is actually the trans resistance part. So M1, M2, M3 is a cascaded common source amplifier. This M4 here is the basically the trans resistance that we use. The advantage of using that kind of topology is instead of normally you use a resistor and in a negative feedback path from input to output, you put a resistor there. But that resistor basically loads your amplifier. Here, this doesn't load the amplifier, plus biasing is easier, and most of the input referred noise comes from that M4, this guy. And it has about 100 kilo ohm resistance at room temperature at a typical corner. And the swing over here is about 10 millivolt, so its linearity is acceptable. And the maximum, I think the current that you can apply is about 100 nanoamp. And the second stage is a source follower, basically to level shift the output for the second stage voltage gain, which is a cascaded amplifier. So, I mean, as you know, this gain depends on the process and temperature, it will vary. And then we have a class AB or push-pull stage here. I should say push-pull to be able to drive a resistive load. And we used zero threshold devices to be able to have a wide swing in this amplifier. And then we have an amplifier here that feedbacks and sets this DC voltage to reference voltage, which was set to VDD over 2 by an internal bias circuit. So this node stays at about Vref, and we use an external compensation capacitor for that loop. And these devices here are just biasing device, diode-connected biasing devices. Just for the information, we discovered that since we use the zero threshold devices for operation, when temperature varied, actually these devices started not to become a diode-connected device, and bias levels shifted, and we predict that this is the reason that why this amplifier failed around 250 or above. And the trans-resistance gain is basically 1 over GM RF, the feedback resistor here, and times the gain of this voltage amplifier right here. So this expression gives the trans-resistance gain of this amplifier. So the way to test it is first, this is the test circuit. Since this amplifier is non-inverting, a positive amplifier, so very small input grows and then creates oscillations. So even you don't put any capacitor there, with the dip package, we observe spurious oscillations. So we ended up creating a golden ceramic type of board, and then placed our die here, and placed an 82 picofarad load capacitor to be able to cut down the oscillations. And this is the compensation capacitor for the DC voltage level setting. And we use a 3 mega ohm resistance for our measurement. What it does is you basically vary your voltage, and then this node supposedly stays about the same. So you inject the current V over this resistor, and then you know your output, input, and this resistance. You can measure what's going on in your amplifier, basically. So this is the measured frequency response. If you look at it, this is an AC response. This is 250, this is 300. So up to 200 degrees, there's not much variation. We did this based on setting our bias current in a way that our trans resistance gain stayed about the same. So even at 250, it's still okay, but at 300 C, it starts to go down. Both the bandwidth gets worse and the gain gets worse. I mean, the first stage here is basically a closed loop, has two complex conjugate poles, and its values, this 1 over GM changes and so forth. So that's why you are seeing all this peaking when you vary the temperature. And this level here is about 7 mega ohm, as I said, up to 200 C. Okay. The next one is our amplifier's output referred noise performance. So we measured it about 10 microvolts over square root of hertz RMS at 100 kilohertz. What that means is it's about 68.2 attofarad over 100 hertz bandwidth with 1 volt peak to peak input. So it gives us about 68 dB dynamic range. But this calculation only takes into account the amplifier noise. This ignores the sensor noise, which, I mean, the sensor will have resistor, and it will have this is a very good optimistic result. The capacitive temperature sensing is basically, the sensor is basically here is the sensor, and then we have a stainless steel base here, and then we have a high temperature epoxy in between. So this MEMS-based capacitive strain sensor, as I said, glued to high temperature epoxy, and mismatch between these two creates a displacement, which is about 8.7 parts per million per degree, and this corresponds to about 1 femtofarad change per degree. So this temperature coefficient mismatch is converted to displacement, and then that's what we sense. So this is the picture of the sensor. So this kind of displacement results in amplified way, this delta W, and here is also another picture of the sensor. So this way movement creates The movement is shown here on the sensing fingers, and this is equivalent to this kind of well-known representation. And in our test setup, basically we have a ceramic dip. We place our trans-resistance amplifier, and this is our sensor, and we use an external single differential converter, and we applied our signal here. And so this is basically input-output relationship, just to show you. So we apply a voltage at 100 kilohertz. This is the input, this is the output. As you can see, the output is about 90 degrees lead compared to input. So based on this, per each, I mean not each of course, but for certain temperatures we applied this, and then we recorded our measurement, and actually we went back to be able to see if there's any hysteresis, and the result was about 1 femtofarad variation per degree, which is what we expected. And I mean, this is the basic calculation way to extract your capacitance variation. This is your input voltage. This is your impedance of this capacitor, and this is the Rn. So we divided by your impedance times the trans-resistance gain gives you the output. So we had 0.28 picofarad at room temperature, the capacitance, and at 300 C it became 0. So it's about 300 femtofarad change over 0 to 300 C. This concludes my talk. I have some specifications which I already mentioned. The technology is 0.5 micron SOI-CMOS by paragram. The gain bandwidth is 8 megaohm by 1.2 megahertz at room temperature. Input referred noise is 3 picoamp over square root of first for the amplifier at 100 kilohertz. Power is 0.66 milliwatt. Die area is just 8500 micron. And sensor coefficient I already mentioned, and the capacitance I already mentioned. Thank you.